Picture this. You've built a smart energy meter that sends household power usage to the cloud. Now imagine someone on the same Wi-Fi network quietly listening to that traffic, capturing your MQTT packets, or even injecting fake commands to your device. That's not a far-fetched risk. It's exactly what happens when MQTT is left unprotected. In this lesson, we'll fix that. You'll learn how TLS certificates lock down MQTT so only trusted brokers and devices can talk to each other. By the end, you'll know not just how to code it on ESP32, but also why certificates matter in real-world IoT deployments. Think of TLS as building a secure tunnel around MQTT messages. First, your ESP32 greets the broker and asks for encryption. The broker sends its digital passport, known as a certificate, which the ESP32 verifies using a CA file stored in its flash. Once trust is established, both sides agree on a session key and every MQTT packet gets wrapped in encryption. Without the right keys, an attacker only sees scrambled noise. This is why you never want to skip certificate validation. If you do, your device could be fooled into connecting to a fake broker that simply claims to be legitimate. On ESP32 you have two main options for secure MQTT. In Arduino, you'll use VFE Client Secure along with PubSub Client, loading your broker's CA certificate directly into Flash. In ESP-IDF, you'll use ESP-TLS and ESP-MQTT, which are more flexible for production but a little heavier to configure. Both approaches require certificates in PEM format, which you can download from your broker. The big takeaway is that the security is handled by the TLS library, not by MQTT itself. Your code doesn't change much, just the way you set up the secure client before connecting. Let's walk through a working example. Imagine you're connecting your ESP32 to the public Mosquito broker on port 8883. After joining Wi-Fi, you configure VFE Client Secure, load the CA certificate, and point PubSub client to the broker. In the loop, the ESP32 publishes a test message every 5 seconds. If all is set up correctly, you'll see confirmation on the serial monitor and the message appearing in a subscriber like Mosquito_sub. The real value here is not the code itself. It's the habit of always wrapping MQTT inside TLS before sending even the simplest sensor reading. In this example, we're connecting the ESP32 to an MQTT broker securely over TLS. First, we include the required libraries: Wi-Fi for network access, VFE Client Secure for encryption, and PubSub Client for MQTT messaging. We define the Wi-Fi credentials and the broker details. Here we're using the public test broker, test.mosquito.org, on port 8883, which is the secure TLS port. To make sure our ESP32 trusts the broker, we provide its root certificate in PEM format. Next, we create a secure Wi-Fi client and pass it to PubSub client. In setup_Wi-Fi, the ESP32 connects to Wi-Fi. The callback function prints any incoming messages from the broker. The reconnect function ensures the ESP32 reconnects if the connection drops and subscribes to the topic ESP32 test. In setup, we load the certificate, set the MQTT server, and define the callback. Finally, inside loop, we reconnect if needed, process messages, and publish "Hello from ESP32 Secure MQTT" every 5 seconds. In real projects, most connection failures aren't coding errors, they're certificate or clock issues. If your CA file is expired, mismatched, or incorrectly copied, the TLS handshake will fail. Another overlooked trap is the system time. TLS validates certificate dates, and if your ESP32 boots with an incorrect RTC, the connection gets rejected. Large certificate chains can also hit memory limits, so trim your CA where possible. Finally, be careful with reconnect logic. Aggressive retries during handshake can trigger watchdog resets. Always isolate these problems by first testing with a known public broker before moving to your production one. Once you've mastered the basics, it's time to stress test your skills. Start by publishing temperature data from a DHT11 sensor securely over TLS and plot it in Node-RED. Next, create a secure command channel where your ESP32 toggles and LED only when receiving messages through the TLS protected broker. For more advanced practice, Enable mutual TLS with both server and client certificates. Finally, intentionally break things. Try using an expired CA or a wrong host name and watch how the ESP32 behaves. Each of these exercises reinforces the fact that secure MQTT isn't optional. It's your first line of defense in IoT. Today you saw how easy it is for plain MQTT traffic to be intercepted or forged, and how TLS fixes that by encrypting communication and validating identity with certificates. You learned how to set up secure MQTT on ESP32 using CA files, debug common pitfalls like time sink or expired certs, and extend the setup into practical mini projects. With these skills, you can confidently deploy ESP32 devices knowing that your data is private, your broker is trusted, and your automation is not at the mercy of attackers on the network.